Hi everyone, in this video we're going to introduce electrochemical cells, and there's two types of electrochemical cells we're going to be studying: galvanic cells and electrolytic cells. Now the focus of this video is just going to be on galvanic cells, also known as voltaic cells. And in these, a spontaneous reaction is occurring. So a battery is a galvanic cell or a voltaic cell that can be used to do useful work. So the reaction that occurs is spontaneous. It generates a current, causing electrons to flow, and the flow of those electrons can operate a device like make a light bulb glow, or in this case just turn the voltmeter reading to 1.1 volts like you can see. On the right, there's an electrolytic cell shown, and that won't be the focus of this video, but just to distinguish between the two, the one on the right is going to drive a non-spontaneous reaction. So instead of using a chemical reaction to generate electricity like we are on the left, on the right we're using a battery to drive a chemical reaction that would otherwise not occur. The goal of this video is just going to be to describe galvanic cells, also known as voltaic cells, qualitatively. So just to describe the components and see what's going on. And you can see there's really two parts. There's one part on the left there which has a copper electrode and some copper sulfate, and another part on the right which has a zinc electrode and some zinc sulfate, and those are called half cells. And they are separated from each other, only connected by a salt bridge. We'll talk about that later, but each half cell is going to be a place where a half reaction takes place. In other words, either reduction or oxidation. Now, typically the half cell that's shown on the left is going to be the anode where oxidation takes place, and the one on the right is going to be the cathode where reduction takes place, although they may be reversed. That's the convention. We're going to separate these two types of reaction, although you can never have oxidation without reduction if something is gaining electrons and something is losing electrons. But we'll often just analyze each half of the reaction separately. They are kept in separate half cells, and the one on the left here is showing oxidation. Again, this is zinc being oxidized to zinc 2+. And notice that, of course, oxidation is a loss of electrons. Where do those electrons go? Well, you can see them flowing through the wire and through the filament of that bulb, making it glow, and then continuing on to the cathode, where reduction takes place. And at the cathode on the right, you can see the copper ions in aqueous solution, which start off as copper 2 ions, are being reduced to copper metal. And of course, reduction is gaining electrons, so as those two copper 2 ions are gaining electrons, they are turning into reduced solid copper. So electrons are flowing from the left to the right. They're flowing from the anode to the cathode, and if that continued to occur, then there'd be a charge imbalance. And in order to complete the circuit and make sure there's not a charge imbalance, the salt bridge is going to allow for the migration of anions and cations in such a way that there is not a buildup of positive or negative charge on one side of the cell or the other, but rather there's a complete circuit in terms of a flow of charge. So the anions are going to migrate towards the anode, and that is because the anode is going to have a positive charge. Notice at the anode where oxidation is taking place, all those zinc atoms are being oxidized to zinc 2+ and going into solution. Well, that will cause a positive charge to accumulate in the solution, and that's why those nitrate anions are going to migrate through the salt bridge and through that bit of glass wool and neutralize the zinc cations. And alternatively on the right, as electrons are being transported to the cathode, the copper ions in solution are being reduced. Well, there's a deficiency of positive charge in that solution as a result, and so the potassium ions are going to flow in that direction to replenish that positive charge, which is being depleted as the copper is reduced to solid copper metal. For that reason, cations migrate towards the cathode. So there's a lot going on here, certainly. We'll have to unpack it step by step. If we zoom in and look at the anode on the left, you can see what's happening there is zinc is being oxidized. And when zinc is being oxidized, you can see the zinc is actually going to leave the metal electrode and become part of the solution. Remember, zinc ions are soluble, but the reduced zinc metal is not. And so as the zinc is oxidized, it's going to go into solution. But on the other side of the half cell, or the other side of the cell, you can see that the copper ions, which start in solution, copper ions are soluble, are going to be reduced to solid copper metal. So it should make sense that as the copper is being deposited on that electrode, it's actually going to gain mass. And on the anode on the left, that zinc anode is going to actually lose mass. So a very helpful analogy that I'll make, or a memory device that I'll refer to, is this an ox and red cat memory device. So on the left you can see an ox, and on the right you can see a red cat's paw print. Why an ox and red cat? Well, because the anode is the site where oxidation takes place. And not only that, but oxidation is going to cause the anode to lose mass. So if you'll forgive the analogy, think of this as an anorexic ox, because it's going to lose mass. The cathode is where reduction takes place. So reduction at the cathode, think red cat. Not only that, think fat red cat, because the cathode is going to gain mass. Why? Well, because reduction is going to cause ions to go from being in aqueous solution to being part of the metal electrode. So this memory device, an ox and red cat, is going to be very useful, not only for thinking about galvanic or voltaic cells, but also for thinking about electrolytic cells. The anode is where oxidation takes place, and the cathode is where reduction takes place. The anode will lose mass as the reaction proceeds, and the cathode will gain mass as the reaction proceeds. Our goal is just to be able to label and describe the processes that are occurring in a galvanic cell. And like I said before, there's a lot going on, a lot to unpack, so let's take it a little bit at a time. First of all, we're going to focus on the left-hand side here. And this animation is going to cycle a few times, and you can see the reaction doesn't start until the salt bridge is lowered into place. And that's an important consideration. We'll come back to that point in a moment. The other thing that you'll notice when the animation cycles again is once the reaction starts, you can see that iron anode on the left is going to start to lose mass. And the reason it's losing mass is because the iron atoms it's made of are going to become oxidized. Of course, oxidation at the anode. And that means they're turning from reduced iron atoms to oxidized iron cations. In this case, it looks like they're turning into iron 2 cations, which are going into solution. And that's the reason why the anode loses mass. So where do those electrons go? On the left-hand side, we have oxidation occurring, and oxidation is losing electrons. Well, you can see the electrons are flowing through the wire, and they're going to the copper electrode, which is the cathode. So if I'm losing electrons, then I'm going to cause these iron atoms to accumulate, these iron ions to accumulate in the iron nitrate solution, and the accumulation of those positive cations is going to cause the nitrate ions of the salt bridge to migrate into that solution so that we have still a neutral solution. Let's talk about the other half of this galvanic cell, which is the cathode on the right. Now the cathode on the right is gaining mass. Why would that be? Because the copper ions in aqueous solution are being reduced from copper ions down to solid copper metal. Reducing is gaining electrons. Where do those electrons come from? They come from the wire as they're being transported through the cell. Now, all of those copper ions in aqueous solution are being depleted, and so that's going to be a deficiency of positive charge in that solution. That's why the salt bridge is going to cause potassium ions to migrate into the solution on the right to replenish the positive charge as the copper ions are leaving. Now, drawing an electrolytic cell is really some helpful thing to practice, but it's a pretty tedious process to draw a diagram like that. For that reason, we're often going to just draw instead a simple diagram or a simple shorthand notation involving these single and double lines. The single line represents a phase barrier, in other words, a difference between a solid and an aqueous solution, and the double line represents the salt bridge, or the separation between the anode and the cathode. Typically in our drawings, the anode will be on the left, and in this convention of shorthand notation, the anode is also on the left. For instance, if we wanted to write a shorthand notation for this particular cell we've looked at, we would start by writing zinc in the solid state, because that is the anode where zinc is oxidized. Anode comes first, and then a single line. The phase barrier separates the solid zinc from the zinc ions in aqueous solution. And a lot of the time the molarity will also be written here along with the state symbol, and we'll assume it's 1 molar standard state. Then the double line is going to separate the anode from the cathode. What is the aqueous solution at the cathode end? Those are copper ions. And what's the electrode made of? Solid copper. So this is an example of how we'd write shorthand notation for a cell, for a galvanic cell. And we'll look at one more example right now. See if you can write the shorthand notation for this cell where cadmium is the anode and copper is the cathode. Pause the video here and write it down, and then check your answer. Here's the answer to that. The shorthand notation shows that cadmium is the anode and copper is the cathode. And again, sometimes in addition to AQ for aqueous, you'll see 1 molar or any other particular molarity that may be involved of those aqueous solutions. We can do this backwards as well, and I'm going to show you a shorthand notation and ask you to try to sketch the galvanic cell. When you're making a sketch of a galvanic cell, it's important to include the salt bridge, because the galvanic cell won't operate unless there is a salt bridge. And see if you can label which is the cathode, which is the anode, and also show the direction of electron flow through the wire. And you can put either a light bulb at the top of the cell or a voltmeter at the top of the cell, whichever you prefer. Remember, this is a galvanic cell, so it's going to involve the flow of electrons spontaneously from the anode to the cathode. Pause the video here and see if your diagram matches the slide that'll come next. So there's a diagram of that particular half cell. There's the shorthand notation once again. The copper anode is in copper solution. The silver cathode is in silver solution, and you can see electrons are flowing from the anode to the cathode. The salt bridge is containing potassium nitrate, and there are many salts that might be used in a salt bridge. Those are fairly common, and you can see that the nitrate ions are going to migrate towards the anode and the potassium ions towards the cathode. Now there are a few other types of electrodes you may see. One that's important to be familiar with is what we'd call an inert electrode. That's one that does not participate in the reaction, but just provides a surface or a site for electron transfer. And most commonly this is going to be platinum, which is a very unreactive metal. It's used whenever a gas is a product of a reduction reaction. For instance, hydrogen ions will reduce to hydrogen gas, and that's a really common type of reduction reaction in a cell. It's also used when the redox reaction might just be changing the oxidation number from one positive number to another one, like lead being reduced from 4+ to 2+. That may be a reaction in which an inert electrode such as platinum is used. Platinum is also used in the standard hydrogen electrode, which we'll talk about a little bit later when we talk about quantifying galvanic cells. But the standard hydrogen electrode, or SHE, is going to involve platinum. And you'll notice that platinum does not actually react, but it's providing a site for the hydrogen ions in an acidic solution to be reduced to hydrogen gas, which is then exchanged here to replenish the supply of hydrogen. So the way that shorthand or notation would be written, you'll notice that the platinum electrode is designated here with the term on the far right, but the aqueous solution that is associated with the cathode is not the same element as the cathode itself. So that's an example of how an inert electrode would be notated in a shorthand diagram of a cell. Here's one more that's a little bit of an exception. You can see that a platinum electrode is being used here, and the solution contains all sorts of ions. And if you remember, the permanganate anion is often going to be involved in redox reactions where it's reduced to the manganese cation, which is 2+. Manganese in the permanganate anion is actually +7 in an oxidation state. So here the manganese is going from +7 to +2. And an inert electrode is actually going to be used here to facilitate the electron transfer involved there. Platinum is very non-reactive and conducts electricity well, so it's going to be used as an inert electrode commonly. You'll notice that this also occurs in acidic solution. You may remember doing a redox titration where we needed to acidify the solution in order to facilitate the redox reaction, so there's lots of different ions involved. And when we write the cell notation for a more complex electrochemical cell like this, you can see that there's many, many different ions in aqueous solution, 3 of them here. They're all listed with commas separating them on the cathode side of this cell notation. So that's an exceptionally complex scenario, but you can see how the convention of writing shorthand notation is still used in the same way. Now, that wraps up our discussion of describing galvanic cells qualitatively, and there's some practice that you should do with that before moving on to describing them quantitatively, where we'll actually calculate cell potential. Hopefully that was helpful, and we'll see you next time.